All right, hello everyone. This is lesson 25, example problem 1. We're going to do 1A and then we're going to do 1B. So for 1A, we have a simply supported beam with a 7,000 pound point load right in the middle of our 10-foot beam. All right, so the problem asks us to solve for the resultant forces at A and B. So this is our point B and this is our point A. So point B is a roller support. Roller supports can only provide a force in the y direction. So on our roller support, we have our By that we'll need to solve for. For point A, we have a pin support. That's what the triangle is. So for a pin support, we can have both a force in the y direction and a force in the x direction. All right, so at this point we have a pretty simple statics problem. We're going to solve it the exact same way we solved statics problems earlier on in the semester. So we're going to do the sum of the forces in the x direction is equal to 0. So in this case, if we look at our picture going left to right, the only x force we have is the x component of force A, and there's no other forces, therefore the x component of A is equal to 0. So that's pretty easy. All right, so next up, so we'll do the sum of the forces in the y direction is equal to 0. So for that one, we'll again start left to right. So we have our AY, we have our minus 7,000 pound point load, and we have our BY. So the sum of all three of those is equal to 0. So at this point we have two unknowns. That's only one equation, so we can't really solve it. All right, so our last statics equation is that the sum of the moments about any point, which is equal to the sum of the distance times forces, is equal to 0. So we have to decide what point we want to sum our moments about. So the best way to do this is to pick a point that's going to eliminate at least one of our loads. So if we can go ahead, we can pick point A, because that way the distance between our y component of force A and force A itself is going to be 0. So we'll have our y component of A times 0 plus, and I guess we also have to go in here, we have to decide what direction is going to be positive. So we're going to define counterclockwise rotation as our positive direction. So our 7,000 pound force will give a clockwise rotation. Our force from B gives a counterclockwise rotation. So our 7,000 pound force is going to be negative, and our force at point B is going to be positive. All right, so for looking at our 7,000 pound force, we have 7,000 pounds, and the distance between that and point A is 5 feet. And then we have our y component of B times the distance between that and point A, which is 10 feet. And that all is equal to 0. All right, so we have By times 10 feet is equal to 35,000 foot-pounds, and therefore By is equal to 3,500 pounds. So we take that, we can plug it into our sum of the forces in the y direction equation, say that AY minus 7,000 pounds plus 3,500 pounds is equal to 0. Therefore, AY is also equal to 3,500 pounds. So does this make sense? We look at our picture, the 7,000 pounds is directly in the middle of our beam. So it makes sense that it's splitting the load equally between point A and point B. All right, so that's our answer for example problem 1A. So if we want to go ahead and take a look at 1B, we have what's called a distributed load going between our point A and our point B on our simply supported beam. It's 700 pounds per foot, and it's spread out over the entire 10-foot distance of our beam. So the way we're going to deal with these distributed loads is we're going to simplify the problem by determining what is the equivalent point load point load for that distributed load. So it's 700 pounds per foot acting over 10 feet. So if we want to find the equivalent force, that's going to be equal to 700 pounds per foot times 10 feet. So the equivalent force is 7,000 pounds. All right, so the other thing we need to determine is where that equivalent point load is going to act. So technically, what we have to do is we have to find the centroid of the distributed load. So we have our distributed load, our 700 pounds per foot, and we would want to find what is the centroid of that. Well, it's a uniform distributed load. It's 700 pounds per foot across the whole thing, and that makes a nice little rectangle. So if everyone remembers your equations for centroids of rectangles, base and height over 2, right? It means that our equivalent point load is going to be acting in the middle, 5 feet in from either side, because that's what the centroid of that distributed load would be. So if we decide to draw a picture with our equivalent point load, that was really bad. Draw our beam, our roller support, and our pin support. Draw our equivalent point load of 7,000 pounds and say that it's 5 feet in from either side. Right? So then at this point, we would be able to go ahead and solve for our reaction forces at A and B. A, again, having both an X and Y component because it's a pin support. B, having only a Y component because it's a roller support. And then at this point, if you look, our equivalent point load for 1B gives us the same picture as our actual point load for 1A. So our solution would be exactly the same. So if we went through, we would find that AY is equal to 3,500 pounds and BY is also equal to 3,500 pounds. All right, so one last note on these ones. This whole equivalent point load method is really useful for determining the reaction forces, finding that AX, AY, and BY. However, that is the only thing you can use the equivalent point load for. Later, in later lectures, we're going to do what's called shear and moment diagrams. When you go to do your shear and moment diagrams, you cannot use your equivalent point load picture to generate your shear and moment diagrams. You have to go back to the actual picture of what that distributed load looked like. All right, thanks.